what I think would be a good place for us to start when it comes to talking about basic counting principles is namely counting elements of sets. So counting elements of sets. So I think this is a rather good place for us to start. We're going to start talking about counting elements of sets. Namely, we're going to be looking at our first of the two basic principles for counting that we're going to discuss here. I thought it would be a good idea I give you an idea where we're going with this. So suppose I give you a set. Now a set is just you can think of it as a collection of objects where there's no duplicate objects in the set, and we don't care about the ordering of them. So we call the things inside the set an element, or elements per plural. And you can imagine, for example, that you have a set and it has elements in it. Now I must stress that we're going to pretend that these are all different elements. These are all distinct objects that are in my set. They could be, for example, strings, they could be numbers, they could be all sorts of things. They could be me, I don't know, at least on an abstract level. Okay. So you can imagine I have here 6. So suppose that I wanted to know how many elements are in a set. Now, of course, I could go through each one counting one after the other, right? Now, imagine that instead of suppose instead that I gave you 2 buckets. 2 buckets. And suppose that one bucket has 3 elements in it. Another bucket has 2 elements in it. And let's throw a third one in here, just to make this fun. Suppose I have a third bucket with 1 element in it. Now, what if I wanted to answer the question as follows? Suppose that I wanted to know how many elements were in all 3 buckets. Well, naturally, one way you could do this is you would ask, okay, there's 1 in here, 3 in here, 2 in there, so you just add them up. Now, one thing that's really important about the way, there's something rather implicit that I did here, right? First, a set doesn't necessarily have it where like you can imagine these as 3 different sets, but there's a presumption that I've made here. First, that each one of these guys are distinct. They aren't actually 2 in the exact same kind in 2 or more of the buckets. So for example, suppose that this element actually existed in, say, this bucket too. If I were to do that, would I end up getting the correct count by following that process? No, because I would overcount this element by 1, right? Suppose that, for example, this is like the number 1, that's 2, 3, 4, and this is 5, but 5 appears both in this bucket, but in this bucket as well. So suppose it's in this one, but it's also in this one too. That's something that's possible with a set that you can't do with a bucket like this unless you literally were only caring about labels on these items, okay? But the point I'm getting at is that we're making a presumption when we put the objects into the buckets, is that the objects behave in a way that they can be put into a bucket, but they don't actually cause it to exist in more than one bucket in the way I've implicitly laid these out, right? So sets don't necessarily have this property. We need to ensure that we actually represent that carefully. What we would describe, what I've just described here for you, is that when I look at this set versus this set, or this bucket against this bucket, they don't have any elements in common amongst each other, right? So we would call these 2 together, they're mutually disjoint, meaning that there's no common elements between the 2. Likewise, I could say the same thing about these 2, and I could also say the same thing about these 2. So what we would do is we would actually talk about this in terms of sets a little bit more carefully. So let's write something down about this. And this brings me to talk about the addition principle. So here's the addition principle. So this is a theorem. We're going to prove it. So consider any finite set A. So A is the name of the set. And remember, the set consists of elements. Now, I didn't say anything about it having no elements or having elements. So it could be empty, technically speaking. So this set is going to have a property. It's going to be similar to our buckets. That is the union. Now I'll explain what that means in a moment. The union of K. So I'm going to imagine I have K. So imagine, think of K as the bucket. So K would be 3 in our example. K distinct pairwise disjoint subsets A1, A2, A3, all the way up to AK. So there's actually going to be K of these subsets. And let me walk you through carefully what this means. So the union, what it means is that you're taking the elements in all of these, you throw them into one super bucket. So for example, like I had all 3 of these buckets. Imagine I took all the elements and I dumped them into one super bucket. Now, the thing that happens when you perform a union operation in set theory is that you don't count the duplicates. So duplicates just sort of evaporate. We don't care about multiplicities of elements. Likewise, we don't care about the order in which you do it, okay? So first, if I put all these elements in these sets go into this one, just like I dump all my elements into one bucket, I just don't care about the duplicates. So it means that I just simply imagine they just don't exist, right? So I just simply could just toss out any duplicate I run into when I'm doing this process, or just simply ignore them. But we don't attribute them to being a part of the count of the elements in the set. So I have K of them, but they're pairwise disjoint. Just like when I talked about the buckets, did you see that it was possible for me to have an element that exists in 2 buckets simultaneously? No, right? Because one had to be in one of the buckets, right? It couldn't be in 3 different buckets or 2 different buckets. It had to be in one bucket. So that means that when I look at my different buckets, so these are actually the buckets here. If I look at any pair of buckets, they don't have any elements in common amongst each other. So that's what pairwise disjoint means. So that means that if I were to take them together, there should be no elements in common amongst them, okay? So there's K of them, and they have this pairwise disjoint property. So it's just like our bucket scenario. So what does that mean then? So remember, we just talked about how we would count this then. Well, how many elements are in A? So a common way to denote the number of elements in a set is using these vertical bars. So this is noting what we call the cardinality or the size of the set A. So the bars here, these denote the size or cardinality, if you want to be fancy-pantsy like me sometimes, the cardinality of the set. This notation is very common with knowing the size of something, like a length of a string. This notation is fairly common. So if I want to get the number of elements in A, that's what this means. What I do is I sum over the cardinalities or sizes of the subsets. And this is exactly what we just described before with the buckets, right? All this is saying is you go across each bucket, you count up how many elements are in each bucket, right? That's what it says. And then this addition principle is saying that actually equals the cardinality of A. And remember, it's because of this condition in play. If we didn't have that, as we're going to revisit, we can't necessarily say this, okay? So we're going to actually prove this theorem. We're going to use mathematical induction to do this. So we prove the claim via mathematical induction. So usually a good idea when you're proving something by induction, you need to state what exactly you're proving and what you're proving on. So in our case, notice that I have I have k distinct pairwise disjoint subsets. So a natural parameter for me to perform induction on is k. So notice that the statement, when I alter k, seems to be the real game changer here when I want to prove this statement, because k is the only variable other than the sets themselves, which we must presume that they're arbitrary, right? This is the thing that seems very natural to iterate over when we talk about induction. So for each k greater or equal to 1, we're going to let the statement S of k, we let S of k denote the statement. So this is what we're going to prove. We're going to prove the following statement. So you're going to see that I'm just going to reframe this. So S of k is if a finite set A equals the union of k pairwise disjoint subsets A1, A2, ... AK, then it has to be that something like this follows, right? Then the size or cardinality of A is equal to the sum from I is equal to 1 to k of cardinality of AI. Right? That's, if we could prove this, then we're done, right? So let's now go through and go about this. So if we could prove this for all k greater or equal to 1, then we're done. Piece of cake, right? So what's the first thing we do in an induction proof? Well, think back to teaching Miss Kitty how to climb a ladder. So what's the first thing you do? Show Miss Kitty how to climb up a first couple rungs, or as many rungs as Miss Kitty needs. They make it easy enough to show how to climb any arbitrary 2 or 3 rungs or more. Namely, go from one arbitrary step to the next arbitrary step. If we could do that, then logically speaking, we could show Miss Kitty how to climb up any number of steps on the ladder, at least if we're thinking about this from an induction standpoint, not from a stubborn Miss Kitty standpoint. So let's see what happens. And then that way Miss Kitty can go nap in the bed, and we proved our statement. So we're going to prove our base step. We're only going to need one here, namely for k is equal to 1. So S of 1 says A is a set that equals one subset. What's the one subset? What is it? What is it? We only have one possible subset. Well, in our statement, we would call it A1, right? But what does that mean if there's only one subset and it actually equals, so if I take the union of all of these subsets, I get A, right? So if I only have one bucket, which is what A1 is, what is this when I take all the elements in A1 and I union them all with the other possible subsets, which in this case there's only A1? Well, it's just A, right? That's all it is. Then A is equal to A1, and because this is the exact same sets, that means that it has to be the case that A, the set A, is equal to the set A1, and so they have to have the same count, right? And so the cardinality of A is the cardinality of A1, and S of 1 holds. So we've proven for k is equal to 1 the addition principle. Now we would like to be able to go an extra step here. Namely, we want to do this inductively, right? So now we got the more interesting part of this claim. So now we have the induction step. So we're going to prove given S of m. So if S of m, then S of m plus 1. So we're going to fix some integer m, which is going to be greater or equal to 1 because we proved it up to 1. So that's why I picked 1 there. You gotta imagine it like I'm climbing up a ladder, but I only go up to and until where the induction needs to begin. So we're gonna fix that and assume that Sm, so S of m, which is going to be, it says if a finite set A equals the union of m pairwise disjoint subsets A1, A2, all the way up to AM, then the cardinality of A is equal to the sum from I is equal to 1 to m of the cardinality of AI. Right? That's what S of m would be, right? So what I need to do is that if this is the case, then I want to show that S of m plus 1 follows from it. So we're going to assume this holds. This is our induction or inductive hypothesis. I'll point out when we use it. Then we prove that, now S of m plus 1 is just simply this, where I replace everywhere I put m with m plus 1. Prove that if a finite set A equals the union of m plus 1 pairwise disjoint subsets A1, A2, all the way up to AM plus 1, then the cardinality of A is equal to the sum from I is equal to 1 to m plus 1 of the cardinality of AI for each AI. So we got to actually, I don't want a period yet. I need to say that this follows, right? Then we prove that this follows. So this is going to be the setup for our induction step. Here we go. So now watch this. Now this is where I'm going to use a little bit of set theory here. So I'll explain this very carefully. So by definition, A is going to be equal to the union of A1, A2. This is what this U represents. It means union. So it means I dump all of the elements of these two into one bucket. I don't care about the duplicates, so I'm just going to pretend they just don't exist, or I just throw them out. And I'm going to do this over all of the subsets. So remember, just think of these as buckets. In fact, that intuition will be very helpful for this proof. So I have all of them. Remember, this is what it says, is that A is the union of all of these subsets. And we said that they're pairwise disjoint, right? So let me write this in set theoretic terms. So what it's saying is that if I give you any two subsets, AI and AJ, it has to be that these, when I look at them, they have no elements in common with amongst each other, meaning that it is empty. So this is the empty set, meaning that there are no elements in common. So this is what we'd call intersection. So these are the elements that would be in common amongst each other. So meaning that they exist in this set and this set. You know how I talked about how I tried to imagine that there was an element that could exist in both buckets at the same time? What this constraint is specifically saying is that if you looked at these two sets, it must be that the ones that are in common, which would be a resulting set after this operation, there's none in this set. That's all it says. There's none in common. So this is true for all. So I got to do this over all of the i's and j's. For all i's equal to 1, 2, all the way up to n plus 1. And j is equal to 1, 2, all the way up to n plus 1 whenever I is not equal to j. So what I'm saying is you can imagine this, you're just looking at every one of the possible pairings of these like we did in our example with the buckets. And I said that there's none in common. That's all this is saying. That's all it says. There's nothing scary about that. It's just, that's all it's saying. So now, I'm going to, so let me give you the game plan of how I'm going to employ induction here. Now remember, if S of M holds, then I know for M subsets, and these are pairwise disjoint amongst each other, that it has to be that they equal the sum of all the cardinalities, right? Of those is what A would be at that time. So what I'm going to do is I'm going to invent a new set that's going to include something a little bit different. So watch this. So let set A prime, so watch this. So I'm going to give that a name. Let A prime be the union of A1, A2, A3. So it's all of the union operations of over all these subsets. I'm going to dump them all into one super bucket. And that's going to be what A prime is. Remember, I get rid of all the duplicates. I don't care about those. They're in common. But the thing is, we don't have any in this case, right? There are going to be no common elements because these are all pairwise disjoint, right? So there aren't going to be duplicates. So notice that both A is equal to A prime union A sub m plus 1, right? Because that's what A is, right? A is the union of all of these up to AM union A m plus 1, right? That's what A is. But A prime is everything up to but not including the last bucket. So A is actually going to be equal to this. And remember that all of these subsets are pairwise disjoint regardless, right? So even if I lumped all of these first subsets all together, then I union this one, they still are pairwise disjoint, so there's not going to be any duplicates, right? So, and A prime intersect AM plus 1 is equal to the empty set, right? They're pairwise disjoint. So, what does that mean about the size of this set? Well, the cardinality of A prime union AM plus 1, this is actually going to be equal, because remember, there's all of these elements. They're on their own, right? From these ones. There's no common elements, right? So if I counted them, it's no different than me examining one super bucket with another bucket. And they don't have common elements at all, so it means that the sum of how many elements are in this set here is just going to be A prime, the cardinality of A prime, plus the cardinality of A m plus 1, right? Now we have the key ingredients to prove the claim. So watch this very carefully. So to prove this, I'm going to start on the left-hand side of S of m plus 1, and we're going to derive the right-hand side. So beginning on the left-hand side of S of m plus 1. Well, what was the left-hand side? It was the cardinality of A, right? But what does that equal? Well, we established in the previous sentence that that is the cardinality of A prime plus the cardinality of AM plus 1, right? That's what it means. But what does that mean? Well, this, if I unpeel this, what can I do with this? What's this? What's A prime? Well, we know that actually the answer to A prime, right? Because of the induction hypothesis. It's the sum over all the subsets, right? Up to M. Plus the cardinality of AM plus 1. But this is by the induction hypothesis, right? So I just pulled out S of M and I say, okay, well, I know the answer to this one, right? That's what S of M is talking about, which equals this. Now all I'm going to do is just bring this in to this sum, and then we're done by adding an extra term into the summation here. So it's a sum from I is equal to 1 to M plus 1 of each AI, which of course is the right-hand side of S of M plus 1, right? Completing the induction step. Completing the induction step. Are we done yet? Are we done yet? So remember, the whole trick here is that I lumped in this cardinality, this number of elements here into here. It's quite intuitive, right? But am I done yet? Not really yet. No, I have one last thing I have to do, because I have the base step and the induction step. I still have to invoke the principle of mathematical induction to complete the proof. Therefore, so this would go just below this, but I've run out of space below there. Therefore, by the principle of mathematical induction, which is a theorem, by the way, we're using that, S of k holds for all k greater or equal to 1. And that completes the proof. That box over there indicates the end of the proof. So you might say, Dan, why do we need to invoke this? Is that because these are the conditions for which you can apply the principle of mathematical induction? That's what does all the heavy lifting, what we talked about with the intuition around Miss Kitty climbing up the ladder to get to the bunk bed to go for a nap. It's the same intuition, but we're actually using it mathematically. I used the M word. I'm a monster. Which is another M word. Okay. So that's how we can prove the addition principle, and it seems really basic, right? This is some of the more basic things that you probably have ever counted before, right? But we verified it formally. So I want to bring us to another way of viewing the addition principle, that in a way that when we think about things in combinatorics, how we might use this. And I must stress that there's many ways you could use just the cold turkey addition principle. But I want to highlight mostly a higher level version of applying this in plain language. Okay. So here's an alternative formulation of the addition principle. So this is an alternative version of the addition principle. Now, suppose, so instead of thinking about sets and subsets, I'm going to think about them in terms of actions or You can even think of it like categories even. But I'll like to think about them as actions. Suppose there are k, and I must stress that these must be disjoint. For those that are statistically inclined, I mean independent. But we're using disjoint in the sense that we talked about actually here. There's nothing in common amongst these actions, okay? So that if you did one of them, it wouldn't influence the other ones, okay? K disjoint actions, A1, A2, all the way up to AK. So far we're looking kind of similar, where there are N1 ways to do action A1. There are N2 ways to do A2, and so on, until there are NK ways to do AK, action AK. So one way you can frame this is as a number of possible ways you can achieve something about this. So let me frame it carefully for you, because with a slight tweaking to this, you get what we call the multiplication principle. So I'm going to focus on the addition principle. Then the total number of ways to do A1 or A2 or all the way up to or AK, up to and includes AK, is the sum of the number of possibilities. N1 plus N2 plus N3 plus all the way up to NK, which this is of course equal to the sum from I is equal to 1 to K of Ni. Do you see how this alternate formulation is the exact same thing we just talked about, right? It's the same idea. It's just an alternative way of describing the same thing to you. Do you see that there's one very important detail about how this is formulated? Is it says the number of ways to do A1 or A2 or A3 or A4 or all and so on or AK. Notice there is an or here. So let me show you an example of how you might use an or like that. So here's a cute example I always like to point at every once in a while when I get a chance to talk about this. Let me give you a cute example of using the addition principle. Suppose you go somewhere for dinner. Suppose you go somewhere for dinner. That dinner's looking a little bit crooked, okay? So the menu has some choices on it for the dinner plate. The menu for dinner has the choice of 3 chicken meals. So these might be like 3 different kinds of chicken dishes. That's what I mean here. 4 beef meals. So these are just plates that have beef in them. 5 pork meals. And 5 vegetable meals. So you're given an opportunity to pick one of these for your dinner, right? So you get to pick your big dish for your dinner. And you have choices from these. So given the opportunity to pick any one meal, what does that mean then? Well, let's characterize this in terms of the addition principle. Let's think about this. So you get to pick any one meal. So how many are there of chicken meal? So notice that each of these looks like an action in our alternate version of the addition principle. We can get a chicken meal, we can get a beef meal, we can get a pork meal, or we can get a vegetable meal. Do you notice how I use the word or? That's a very helpful phonetic way of remembering when you might need to add as opposed to doing something else. So, what does that mean? So there are 3 ways to pick a chicken meal. There are 4 ways to pick a beef meal. There are 5 ways to pick a vegetable meal. So what does the addition principle tell us? If I have the opportunity to pick any one meal, so I'm picking one, how many are the number of ways to pick a meal? What's the number? Don't overthink this. So remember, you're sitting down at a restaurant. You're going somewhere, you're going to have something to eat. You look at the menu. And you see that, okay, there's these chicken meals, you have the beef ones, you got the pork ones, and you got the vegetable ones. So how many are there? How many ways can you pick a meal here? Well, think of it. You have a menu in front of you. So imagine you have a menu in front of you. You only pick one of them. So how many things are on the menu that you get to pick from? It's the sum of these, right? It's the sum of them. That's exactly what the addition principle would tell you, right? Which is very intuitive. By the addition principle, the number of ways to pick a meal is as follows. It is 3 for the chicken meal, right? 4 for the beef meal. 5, let's see, what do we got here? Oh, I got the pork one. I gotta get pork in here. I knew I forgot one. Ways. I was looking at the board, I'm like, no one's saying anything. I better bat it in. 5 ways to pick a pork meal. So we got 5 for the pork, 5 for the vegetables. So that means that's 10. That together is 17. And this is really intuitive for this scenario, right? Because you can imagine you have a menu in front of you and you ask how many possible dishes can you get for dinner? Well, you just simply count up how many are there, which is the same as doing one of these, right? Sorry, I'm just getting really excited. Not for the meals, okay? I'm just talking about the counting. So that's an example of applying the addition principle. The key thing is that it's about that you get a choice. It's I do this or I do this. It's not I do this and I do this. That just remember that those are not the same things. And it also matters that these are not related to each other in the sense that if you pick the chicken meal, that it actually, one of these meals is also a beef meal, for example. Like it's chicken and beef. That would be a little bit of a problem, which I'm going to talk about now. So let's go through an example of what I'm talking about. So we're going to just first blindly apply the addition principle, and then we're going to see what happens, okay? Suppose that I give you, so we have to be careful So be careful when using the addition principle. So just remember that those sets, those subsets, or actions, they must be disjoint. They're mutually disjoint. So example, suppose that I give you two like this. Suppose that A1 is A1, 2, and 3, and A2 is 2, 3, and 6. Equivalently, you can imagine this like I said in my example over there. Imagine these are the chicken meals, and these are the beef meals, and these numbers represent the item, the index in the menu. So some restaurants actually use numbers to indicate the items on their menus. So, sorry, I thought I heard something fun. So these could be the indices of those menu items. So notice that in our example here, we have a bit of a different thing going on here. Do you see what's going on that's a little bit different than something we consider for the addition principle? Well, let's go ahead in and see what happens. So if we apply the addition principle, then what does it say? So it says that the number of elements in A1 union A2 is what? Well, the number of elements in that one is 3, and that one also has 3. Is 3 plus 3, which equals 6. But is that correct or incorrect? This is wrong, right? Why? Well, let's write out what A1 union A2 is. So this is wrong. No, guys, don't do that. Don't do that. Why? Because A1 union A2 is 1, 2. So we got 1, 2. So notice I have 1, 2, 3, and I have a 6. So the number of elements in A1 union A2 is actually 4, not 6. What did I do wrong? What's wrong with this? What did I do wrong? I overcounted. So I'm overcounting by counting duplicates. And remember, we said that we don't count duplicates. That's something we said near the beginning of this. We don't count those duplicates. Those darn duplicates, we don't count them. So what do we do? So what exactly is going on here? So let's think about what this means then. So which ones are common amongst the two? So which ones are in common between A1 and A2? Well, if we take the intersection of A1 and A2, as we discussed previously, I want the ones that are in both A1 and A2, as opposed to the ones that are in A1 or A2. Well, look, when I underline 2, I underline 2 over here. I had 3 over here too. So notice that 2 and 3 are common amongst the two. Those are our these ones I counted. I actually technically counted them twice. It's a mistake. So I have to account for these. I have to account for those elements. So there's our extra 2. So those are our extra 2, as 6 minus 2 is equal to 4, right? And this is the correct count. So does anyone have any ideas of how we can actually generalize this idea? Well, I'll let you think about it, and let's head over here. Okay. So now, this brings me to talking about a theorem that generalizes over the addition principle. Now, because it requires me to give you more set theory, I'm not going to prove it, but I'm hoping that I've convinced you of what and where it comes from. So here's a theorem. This theorem is called the Inclusion-Exclusion principle. You'll see why it has this name. And I'm going to state it for 2 sets, but the principle still applies more broadly, okay? So you can state it for 3 sets, you can state it for 4 sets, you can state it for any general K many sets. But I think seeing it for 2 sets gives you enough of the idea. So that if you ever needed a more general version of it, you get the idea of how you'd go about it. So if A and B are finite sets, then if I take the union of A and B and I ask how many elements there are, well, we can walk through the same exercise we did over here, just more generally. I can take all the elements in A, the number of elements here, I add them to the ones that I have here, the ones in the other set. But as we previously seen, take note that I did not put any quantifiers on A and B other than that they're finite sets. They may not be mutually disjoint or pairwise disjoint sets. So we're going to have a scenario just like the one we had over here. So I'm going to get rid of the elements just like I did over here that are in common amongst the two. So I take A intersect B. So these are the elements, the number of elements in A. These are the number of elements in B. And these are, of course, the number of elements both in A and B, which you could think of, like we talked about, they're the duplicates.